Welcome to part 2 of trying to wrap our minds around how to understand proton NMR spectra. So in this video, we're going to look at integrations and see how we can understand each peak represents a certain number of hydrogen atoms. So let's take a look. We saw this spectrum in my last video, the first one, the introduction on proton NMR. And just remember that in this particular spectrum, we have one hydrogen that's on the alcohol, and we have 3 of them that are equivalent, chemically equivalent, on the methyl group of methanol. So these 3 red hydrogens are the same distance from everything else in the molecule. They're all the same distance from the oxygen atom. And so they all have the same electron cloud on each of those hydrogens. This electron cloud's a little bit bigger than the blue one because the blue one, the electrons are being sucked away by that oxygen atom. So the ones that are more shielded, the ones with more oxygens around them, they show up farther upfield or more to the right in the NMR spectrum. And those that are more deshielded or fewer electrons around them, like the alcohol proton, might show up more downfield. In this video, though, what we want to understand is that when I have 3 equivalent hydrogens and they all show up in the same place, this peak is 3 times bigger. We'll write 3H because it represents 3 hydrogens. It's 3 times bigger than this blue peak, which is 1 hydrogen's worth of peak area. So what we're measuring is the area underneath the peak. Not how tall the peak is, but the area underneath it. And the way we do that, usually in an NMR spectrum, is we ask the computer to measure the area underneath that peak for us. Now we know from math and calculus that the area underneath a peak is the integral of that peak. So we call that integration, or the integral of that peak, the area underneath the peak. So the bigger the peak is, the more area it is. It tells us the relative amount of hydrogen atoms that peak represents from our molecule. Okay, so let's take this lesson and let's move on to the next spectrum. Here's a little problem. Methyl tert-butyl ketone. And I want you to recognize that there are these hydrogens that we represent with B. And over here on A, there are 3 equivalent methyl groups. So that's A. Now I want you to figure out which of these peaks represents A and which one represents B's hydrogens. And of course, I think it's pretty easy to see that the smaller peak will be the 1 methyl group, and the bigger group peak will be the 3 methyl groups. Now here's the thing I want you to notice. When I measure the area underneath the peak, the computer came back and said, this represents 1 hydrogen's worth, and this represents 3 hydrogens worth. Now that might throw somebody off. They might think, well, this really means only 1 hydrogen and 3 hydrogens. But no, it means there's 3 hydrogens compared to 9 hydrogens, or a 3-to-1 ratio. So it's only telling us the ratio. It doesn't tell us the absolute number of hydrogen atoms. So 9 to 6, or 9 to 3 in this case, is the same as 3-to-1. That would be represented with the 3 hydrogens and the 1 hydrogen peaks. Now, if we did all of this and we saw, let me erase some of these. So let's say we did we asked the computer to measure the area underneath those, and the computer came back with, I think this is 0.5, it says, and I think this is 1.5. You would look at that and would say, well, that doesn't make any sense. We can't have half a hydrogen or 1.5 hydrogens. So you might realize, oh, that's the same as 1 hydrogen to 3 hydrogens, 1 to 3 ratio, which might mean 1 to 3 like it did in methanol, or it might mean 3 to 6 like it does in methyl tert-butyl ketone. So that's integrations. That's it. Pretty simple. So I hope that's helpful. Each peak represents different types of hydrogens with different electron densities around them. And how big the peak is represents how many hydrogen atoms that part of the molecule is being represented by. We'll get into more complicated things here in a bit, but that's a good place to pause. That's the integral or the integration of the number of hydrogen atoms in our molecule, the different types we have. All right, hey, if this is helpful for you, please like and subscribe so more people can find these videos and learn more about organic chemistry and get coached up.